Swayam Prabha. Digital India. Educated India.
Welcome back. We have done predicate semantics. Now we need to understand one very important thing. So far we have been doing the first order predicate calculus or the first order predicate semantics. Why is it the first order? Because I could use a predicate. We never had a variable. So we had variables like x, y, z, that is one series. We also had variables like v1, v2, v3 through vn, that is another series. But all these variables stand for individuals. None of the variables stands for a predicate. Why? It is because we did not want to talk about predicates. We wanted to predicate a property of an individual. We wanted to say something about an individual, but we did not want to say something about a predicate. For example, when we say that Russell is a philosopher, we talk about Russell, who is an individual, and we are saying that he is a philosopher, but we are not saying anything about the predicate philosopher. That is the reason we did not need any variable to talk about predicates. All our variables have been so far individual variables, and we had constants of two types, predicates and individuals. Now we want to also talk about predicates, not just individuals. How to talk about predicates? For that we need higher order predicates, that is predicate of predicates and predicate of predicate of predicates and stuff like that. Doing that is not very easy. So in a sense we are going towards a type theoretical language. But what is the problem with such a language? We shall see that first. So we need to talk about Russell's mathematical theory of types, and then we will go for L type. In a semantics course, it is enough to understand how L type is constructed, but we are talking about Russell's type theory because it is so very important. It is important not only in the field of semantics, but also in the field of logic and computer science and mathematics. Anywhere you deal with variables and constants, you need the mathematical theory of type. It is such an important invention. A very little history of it, which is very important for us, how it started. So it started with this problem which is called Russell's paradox, but before that we can talk about something else called liar's paradox. What is the paradox of the liar? The liar says that I am a liar. This is a very old paradox, but then this paradox actually appeared in a mathematical form when George Cantor came up with his set theory. So what is set theory? What is a set? I can say, for example, that C is the set of all cats such that C is the set of all x such that x is a cat, right. I can, this is how I express the the set of all cats. What do I say? Now, the set of cats in the Cantorian set theory could be expressed like this. This is a condition. It is the set of any x such that x is a cat. Now, how the membership is decided? I take a cat. For example, I take another set M. M is a set of all x such that x is a man. Now, I plug in a constant here at both places x. So, I plug in R, which is Russell, and I see that R or Russell, the sentence that comes out of it is Russell is a man. If this condition sentence comes out to be true, then this thing belongs to the set. This is how we decide the membership. Now, yes, it is true that Russell is a man, therefore, Russell is a member of that set, but for example, we can take I do not know, we can take Indira Gandhi. Now, if you plug in Indira Gandhi here, you see that Indira Gandhi is a man. Now, because the resultant sentence is not true, Indira Gandhi does not belong to the set M. This is very plain and simple. So, we write the variable here, and this is a bar, and after the bar we write the condition, that is, that variable is something. This is a set condition. This is how Cantor set up his sets. So, this is how you could, this is called the naive set theory. So, this is how you could write a set before Russell came up with his great paradox. Now, what is Russell's paradox? Let R be the set of all x such that x does not belong to itself. So, R, remember, is a set of all sets that do not belong to themselves. So, because nobody prevents me from writing a condition like this, Cantor never said that you cannot write a condition like this, but the problem then is whether this set R belongs to itself. Now, this is fine. So, so far it is fine that R is a set of all sets x such that x does not belong to itself. The problem is then R also is a set. So, if R comes here, as if R is plugged in here, we get R does not belong to itself. Now, R then is a member of R belongs to R if and only if this is true, that R does not belong to R, right, because this is the whole point, that this is what we have written here, that in order to belong to the set R, our set has to non-belong, if you call it non-belong to itself. Now, is R a member of R? Suppose R is. If R is a member of R, then R does not belong to itself. Is R not a member of R? In that case, if R is not a member of R, then R belongs to itself. So, because any set, the supplementary set is constituted. So, it actually consists of all sets that belong to themselves, right. So, so this is the problem, this is the paradox. R belongs to itself if and only if it does not belong to itself. So, this was a mathematical version of the liar's paradox we just mentioned. Now, we get we talk about the liar's paradox in details. What exactly is Russell's paradox doing? After Russell came up with this paradox, mathematician revised the entire set theory, and we have many different versions of set theory after that. After Russell came up with this paradox, we have to somehow prevent, we have to somehow block this paradox. in the ordinary language, this paradox appears as the liar's paradox. What is it? So, for example, a man says, I am a liar, or I am lying. Now, this sentence is true even only if it is not true. Look, here you can see the similarity. This is an ordinary language counterpart of Russell's paradox. So, the oldest form of this paradox was from Bible. Bible talks about a Cretan called Epimenides, who claims that all Cretans are liars. Now, the problem is, if all Cretans are liars, then Epimenides himself is a liar, and in that case it is not true, then he is lying, and in that case it is not true that all Cretans are liars. So, this is the problem. You can see the self contradiction inherent in cases like this in the liar's paradox. Now, can you determine the truth value of such sentences? Definitely not, because yes, it seems they are entitled to a truth value, but the moment you want to determine the truth value, you find contradiction. So, what to do with these sentences? We do not want these sentences in our system, because it will in a sense corrupt the whole system. In order to block such sentences, there is a tool was invented, which is called the theory of types. There were many other paradoxes like the liar's paradox, like the barber's paradox, Richard's paradox, and so many others. They have a very we need to first study these paradoxes in order to understand these. So, they have a very special feature. These are all self-referential or reflexive, which means that each of them somehow refers to itself. Each talks about itself. How? Suppose S. Let us call the sentence, all my propositions are false, S. Now, the proposition S is self-referential, since it is about every proposition I make, and it too is my proposition. Now, the problem is, all my propositions are false, S is my proposition, hence S is also false, hence it is not true that all my propositions are false. These are the steps of these are the steps that lead us to the contradiction. Some logicians wanted to exclude such sentences from their logical systems. You need to, otherwise the system will be bad. Russell's theory of type helps us do that. The question is how. Russell defines a type as the collection of arguments for which a propositional function has values. What does it mean? It means that suppose a propositional function. What is a propositional function? Something like m x. It is a function. Why? It takes a value and yields a statement. For example, it takes R, meaning Russell, and yields a statement that is Russell is a man. Now, all the things, all the constants m can take would somehow constitute one type. All the things mx can take, mx can take would be then one type. And so in order to determine one type, we need to collect the propositional function that takes actually those. Now, once again I put it very lightly, very lucidly, and while doing so I am afraid I may mistake, I may make some technical mistake, but it is okay, because we first need to understand this and then we correct the technicalities. So, to start with, we will be slightly loose and somewhat incorrect also, it does not matter. The type of a variable can be fixed by all the values a function is concerned with. So, for example, whatever can replace x would belong to one type. Consider an elementary statement. Russell is a philosopher. that expresses the proposition PR. This is the proposition and this is the statement. How do we distinguish? A proposition is the logical form of a statement. So, it means that R is a member of the set whose members are P. Now, P is the predicates and R the subject of the proposition. So, this is a subject object subject predicate sentence or statement or proposition. Actually, a proposition is different from a statement or a sentence, but we sometimes use them interchangeably, although we don't intend to, but it's okay sometimes. The difference is, for example, I also mentioned that then it will be easy to understand where we should not be doing that. So, then we can do it loosely. Now, what is the point? The point is, for example, John says that I am 6 feet tall, and Nirmalia says that John is 6 feet tall, and Mary tells John that you are 6 feet tall. You see, these are all different statements because they have different grammatical structures, they have different phrases and everything, but all the three statements, that is, I am 6 feet tall when John says, and John is 6 feet tall, and you are 6 feet tall. All these statements actually have a shared logical structure, which is the entity John is 6 feet tall, right. So, if 6 feet tall is is the property X, then it would be Xj. This would be the proposition underlying all these different statements. So, yes, there is a difference, but sometimes we call this the statement, or we call this the sentence. So, we shall also know, we should know the difference between all these terms. Now, as we said that this would be the predicate and this the subject. Predicates say something of the subject. Thus, saying that X is Y means that X is a member of the set, each member of which is a Y. For example, as we have seen when we say that Russell is a philosopher, we do this. A formula whose subject is S says something about X. In other words, it predicates something of X, it attributes a property to X. Now, PR and PX say something about R and X respectively. Such individuals like R and variables like X form the lowest type in Russell's theory of type. Now, we are slowly considering the hierarchy. So, what is a hierarchy? It is a structure where you have the lowest layer and then a layer slightly higher than that, and kind of this is a hierarchy where we are assuming that they don't belong to the same level. In the hierarchy of type theory, the individuals such as R, C and G, say R is Russell, C is whatever, G is whatever, we will see later, are and the variables X, Y, etc. belong to type 1. So, type 1 things are, so the lowest level you find R. These are all individual variables and also individual constants, they belong to type 1. And a variable of type 1 can be replaced only by variables and constants of type 1, that is a rule, we will see that in details. Type 2 consists of x2, y2, p, etc. So, then at this level, here you have x1, y1, at this level you have we add 1, that is better for us. At this level you have P, that is philosopher, M, man, W, woman, and x2, y2. So, now the moment you see 2, you know that it is one level up. So, they represent sets of individuals, and now in Russell is a philosopher, Russell represents an individual while philosopher somehow represents a set. each member of this set is a philosopher. We have seen before that saying something about X means describing X as a member of or a non-member of a set. In a formula, the type of the predicates must always be one step higher than that of the subject. Russell belongs to type 1 because Russell is an individual, whereas philosopher belongs to type 2. If I wanted to say something about philosopher, I would have to use a predicate of type 3. Now, we have seen that this type 3 things were not there in our semantic system. We are going to introduce those. That is why we are doing the whole exercise, but we must exercise caution before doing that, because if we are not cautious, then some paradoxical situations will be there. Now, the relevant rules are R1 in the formula alpha beta. If alpha belongs to type n plus 1, that is one step higher, then beta must belong to type n. Once again, this is put very loosely. Russell's rules are way more stringent and formal, but we are doing it informally. A variable of type n can be replaced by a variable or constant of type n only. Now, let us consider the formula y2 x1. 2 means second order, that is second level variable. 1 is lower, right? The lowest type is 1, and then it is x2 or whatever y2, and you have r here, but here you have p, and here we have something. I am not writing what those are. From this formula, that is this, one can derive y2 y1 because x1 can be replaced by y1 because they belong to the same level, or y2 r also belongs here. One may also derive p x1 because p and y2 belong to the same level, or x2 x1 or p r, but one cannot derive y2 x2 from x2 x1 sense. That would violate R2. Why? Because x2 is a higher type, it cannot replace x1 anyway. So, it will be a violation of R2. That is why this is banned. This construction is sort of prohibited. The point is, how are these rules connected with the self-referential propositions? How do they prevent those things from happening? This is how they do it. Let a proposition that does not say anything about another proposition be a primary proposition. For example, we have P r, which means Russell is a philosopher. It is a primary proposition. Suppose these propositions belong to class M. A proposition that would say something about a proposition of class M would belong to class M plus 1. Thus, we can think of an infinite series. So, propositions of, so P m is proposition of class M, then next level will be proposition of class M plus 1, and then the next level will be proposition of class M plus 2, and so on. So, this is how we can think of an infinite series. All the primary propositions can be represented in terms of the symbolic formula x2 x1. So, what is the primary proposition? It can be interpreted as x2 x1. So, what will come under this? It could be P r. You see, P belongs to the second level, r belongs to the first level, or x2 y1. This also is fine, same level, or mr, or wi, say I stands for Indira Gandhi, and w you know what. So, w stands for a woman. So, and all that stuff, and now x1 cannot be replaced by a proposition, since x2 x1 says something about a member of type 1, that is an individual, not about anything else. We remember this. What is a primary proposition? It has to have this format. or to be more precise, this format. Now, this x1 cannot be replaced by the proposition itself. Similarly, Zm in the proposition Zm is false can be replaced only by a proposition of type M. Thus, if we follow the theory of types, then the meaning of the proposition all my propositions are false would be all my primary propositions are false. That is, all my propositions are false, this proposition itself cannot be my proposition. So, not that all the other propositions and this proposition belong to the same level, they can't, because this proposition is talking about other propositions. So, how do I translate this? When I translate in my interpretation, I make sure that this proposition will not come under all my propositions, because it is not a primary proposition, it is about a proposition. And what is a primary proposition? A primary proposition is something like this, like Russell is a philosopher. The proposition is about the primary propositions, I am reading this, and cannot be a primary proposition itself. In other words, all my primary propositions are false belongs to the class M plus 1, since it talks about propositions of class M. It cannot say anything about itself, because it cannot say anything about a proposition of class M plus 1. So, because it talks about other propositions, it will not come under itself, it will not be self referential. We are doing it, we are reinterpreting this sentence because we have to. What is our tool for doing it? The type theory. Without the type theory, what happens is this proposition and all other proposition somehow do belong to one level which is not desired. Okay. So, then this is just a quote from Russell where he talks about it. Elementary propositions together with such as contain only individuals as apparent variables will call first order propositions. We have thus a new totality, that of first order propositions. So, at the first level we have things like Russell is a philosopher, or x1 is a philosopher, or anything, or I do not know, M is a minister, or precisely x2 x1. Now, what is the secondary proposition? Where the secondary proposition will be so if they are 1, then the secondary proposition will be something like P, like this very special P or this very special M, whatever, which will talk about which will talk now about mx, right, a primary proposition. So, it is a special way of treating propositions, but definitely this special P or special M will not belong to this level. So, it is level 2. So, so this is the order Russell talks about, and then you can read this quote. It is from this mathematical logic as based on the theory of types, which was published in 1908. So, our discussion was sort of based on this paper of Russell, and this quote is very important for us. Now, we can see that how it prevents the paradox, that is the liar's paradox or Russell's paradox. As far as sets are concerned, a set will not have itself as a member. The set has to be constructed in such a way that it will never talk about itself. And if you see the old construction, set R is a set of all x such that x does not belong to itself. The very construction whether R belongs to itself will be impossible now under the new theory. So, this is how set theory was revisited, sorry, it was revised. It was revised in such a manner that you could never write R belongs to itself. It would be a typical mismatch and it will not be allowed. So, Russell's type theory is that blocking tool, the tool that blocks such constructions. We will see how it blocks such constructions. We will have will not go directly to the L type. We need to understand a few things about it, and then only we can go to L type. Okay. So, what is L type? L type is a language based on the mathematical theory of types. Now, we will see the formal part of it. Before we go to that, we shall consider the informal part of it. What is the informal part? It is something like this. So, the type theoretic language will help us do two things. Two features now will be added, two features that were not there in the previous system. So, the first thing is we will see how different types can be constructed. We need to construct, we are ideally supposed to construct infinite types, and we also see to it that a type does not take itself or a higher type as its argument. What do I mean by that? As I said that p x as a propositional function takes say r as an argument and then makes p r, which may be interpreted as Russell is a philosopher. Now, we need to make sure that it never takes p itself as an argument and make p. This is blocked, this is impossible. We are not going to allow this construction. How to do it? So, you see that Russell's type theory helps us actually achieve both the goals. We can create higher types. How can we? We will see that. For example, one simple thing is, yes, we can put it in the hierarchy. For example, x 1 through whatever z 1 and r s t, whatever we know r is Russell. Yes, I don't know, like whatever you read here, and then we have x 2 through z 2, and then you have p philosopher, man, woman, and you have x 3. We do not have many counterparts of x 3 and x 4 and stuff in our ordinary language, but ideally already you are able to create those mathematical elements here for. But yes, this is a device that helps us already create such mathematical elements, ideally speaking. Now, we shall see how type theory is understood. So, this is the most basic part of it, the definitions of types. We have two basic types, and based on those two we will construct infinite types. What are the types? One is d e, that is the set of all entities. You know, the set of all entities is actually A. A is E 1 through E n. From the type theoretical perspective, we call that d e, and then d t is another set, but not of entities, of truth values 1 and 0. Now, what is the device that will help us construct any type? That is, for any syntactic categories A and B, any syntactic categories D, A, B can be constructed. That is, now see, if we remember the definition of a formal system, we can say that here. How is it formal? We start. So, what is our available categories? Just two, E and T, right, nothing else. And the lower type comes first, then the higher type. So, first comes, so you see it is A B. So, first comes the lower type, then comes the higher type. So, or first comes the E type, then comes the T type, if they can be constructed such. Okay. So, now I construct, for example, I have two categories, I have E, I have also T, these are there. From this, what can I construct? I construct also T to E, why not? But I can construct E to E, not that there is that way, there is no hierarchy. I am sorry, I just stupidly mentioned that kind of a thing. Nothing like that. We can construct anything. We can have T to T. Also, we can have E to T or T to E. Now, our linguistic elements are such that we normally do not find T to E. We'll see whether we find, but do we find other things? What is this E type? Anything, Russell or John or anything is E type entities, right? And T type, any truth value 1 0. What is E to E? We don't know, we'll see that, but E to T is very easy. How do we construct E to T? We'll see that all 1 plus predicates. So, this is the second, this is the first step of the recursion, that is the first steps are E and T. Then we can have all these things, E to E, T to T, E to T, T to E, and all that. What could be E to T? We'll see. Now, we'll just we take some time for seeing that, but we'll see that all 1 plus predicates, like for example, philosopher or smokes or man or woman, all these 1 plus predicates actually do belong to this type. We go to a slightly higher level, we can have, we take E from here because E is a type, and also E to T is a type. We can construct E to T. Is there any counterpart for this in the ordinary language? Yes, there is one. Not there is one, there are huge. There is a huge number of such things. For example, any 2 place predicate would belong to this. For example, eats, because loves, because there are 2 things, right? One E and another E, and then finally the truth value. We will see how these work. What about this T to T? It takes a T and returns a T. For example, the sentential what you call this logical operator neg is a T to T thing. It takes a T, it returns a T. We can see that now any linguistic element we can talk about would have a type, right? This is very important for us. Now, this thing we don't know whether anything corresponds to this. We'll see this later. We don't even know whether anything corresponds to this, but we definitely know that these are absolutely useful types. These are absolutely useful types, all these things, and many more. Now, the first step towards a theory of type is to revisit what already we have done from the perspective of this type theory. We are rewriting the entire grammar of L1, which is the simple predicate semantic language. We are going to rewrite the whole language in this type theoretic through this, or rather within this type theoretic framework. What are the things we have? Constants of the category E, D and J and M. Variables of the category E, we know that we have variables only of one category all the time, category E, because we don't have any predicate variable here. So, x, y, z and stuff like that. And then we have categories, constants of the category constants of category E to T, like M and B, which are 1 plus predicates, if you remember. And then the 2 plus predicates, they belong to the category E to T. They are K and L. So, M can be interpreted as say man, B bald, K no, and L loves. So, and then we go to the formation rule. Since we have limited types here, we don't have anything else. We can easily see how it works, because the type theoretical language L type is slightly abstract. So, we need to start with something solid and then we go to the abstract thing. So, to start with, we go for this thing. So, if delta is a member of category E to T, which is a 1 plus predicate, and alpha is a member of the category E, then delta alpha is a member of the category T, which means that when something belonging to E to T, roughly speaking, takes something that belongs to E, it gives a T. So, the second element comes out. So, if this is the construction, you give the first element. If you give the first element, then the second element comes out. So, this construction rules out something like E to T to T. Nothing will happen if you do anything like that. You see, already blocking is an operation. That is, there is some kind of blocking, some blocking is created through the rules. Now, the second rule says that if gamma is a member of the category E to T, that is 2 plus predicates, and alpha is a member of the category E, then gamma alpha is a member of the category E to T. So, precisely it is the category E to T, and it takes the category E and yields E to T. This is what we desire. Now, we actually see the voice of L1 here, because what is L1? L1 is precisely this. So, a sentence goes to N and Vi, and Vi may go to Vt and N. Now, we can put types here. So, finally, S will be the type T, of course, because any sentence, any formula would belong to this level, and N will be E, because it is noun. And now, what is Vi? You see, E to T will take an E and yield a T. So, this is fine, and this is E and this is E to T. So, this is E and this is E to T. This is how I already construct. So, I can see how exactly the structure of L1 is getting recreated in this framework through the type theoretic story. We do not need the rules of L1, we have these new rules, but remember, these are still very specific rules. These are not as abstract as they can actually be. So, we are not using the full potential of these rules, but we are using them for describing one language of semantics, that is the language of predicate calculus. And then if phi and xi are members of category T, then all these things, that is neg phi, phi and xi, phi or xi, phi implies xi, and phi if and only if xi are members of category T. Definitely they would. If phi is a member of category, because they are all statements or formulas. If phi is a member of category T and u is a variable of category T, then all u phi is a member of category T. What does it mean? It means that phi can be anything. So, if phi is any kind of a formula, so it can be mx, or it can be this is what we can make, or it can be Lxy. And then if u is a variable, so we have a variable, say y. So, all y mx is a formula, and all y Lxy is also not that, of course, it is a formula, but more than that, it belongs to the category T. That is, it belongs to the level where a statement belongs. We are not saying that these are statements, but they belong to the same category as the statements do. Now, these are all T. remember that it allows us a construction like this, and once again this quantification is vacuous quantification, because y is not binding x, but still this construction is absolutely fine. You can construct a formula like a y m x. Also you can construct a formula like a all x m x. Both are correct formulae, but it is not a statement, whereas this is a statement, because here binding takes place, if you remember. But here, because there is one free variable here in the whole construction, it is not a statement. We need to sort of revisit whatever we have seen so far in this through this language. And similarly we can construct some x mx or some y mx, or all x some y l x y. All these are formulas in our language. So all these would belong to T. So that is what they are saying. Mx belongs to T, x belongs to x is a u, and this is a quantifier which is just introduced. If that is the case, then the whole thing will belong to the same type, that is T. So we go to the next level, semantic values of the basic expressions. If u is a variable, then u's value will be determined by g, as we have seen the value assignment function. The value assignment function gives values not to the constants, because constants have different values, but to the variables. And if alpha is a non-logical constant, then its value, for example man, woman, or that is, we have at least four non-logical constants. We have m and b, which are 1 place predicates, and l and k, which are 2 place predicates. So these are, so their values are given by f. Also we have constants of type 1, which are this d, n, j, m. These are all non-logical constants. So m, b, k, l, d, n, j, m. These are our non-logical constants, and their values are fixed by the function f. So these two main functions we have. Now we look at the semantics of it. So if delta is an expression of category e to t, that is 1 place predicates, and alpha is an expression of category e, then delta alpha, the value of delta alpha, will be with, of course I'm not talking about the index which is always there, which is m comma g. It will be this, that is alpha, as an argument. So these will be the final value, which precisely means that if you have a construction like mj, then the value of mj will actually be the value of m, which takes the value of j. Here m belongs to e to t and j belongs to e, and mj belongs to, this whole thing belongs to t, that we can see. If gamma is an expression of category e to t, that is a 2 place predicate, and alpha is an expression of category e, then gamma alpha is this construction, which means that if we consider a structure like, just erasing takes some time, but we cannot go to the next page. So yeah, fine. So precisely it says that when we have a construction like loves John, that is in English, but in our language we can have something like L, and L can be anything. L takes, you remember that with L what comes is the object, not the subject, L and J. So if this is our case, then the value will be, so this is e to t and this is e when they come together. So, when you have a construction like L LDJ, which actually means that LDJ means that D, say we interpret it. So, D loves J. I forgot the denotations of D and J, but this is a rough thing. It would first take D as we know, and then it would take L and J. This is how the whole thing is constructed, right. So, the types will be like this. This is E, this will be the type E to T, this will be the type E, finally this is T. So, you see everywhere, look at this operation. The first element are the same, the second element goes out. Once again the first element are the same, the second element goes out. So, this is how it is constructed. If phi is an expression, I am reading these rules, if phi is an expression of category T, then neg phi, the value of neg phi is 1 if and only if the value of phi is 0, that because it is negation. Similarly, for these things we know that this will be 1 if and only if both phi and psi are 1, here at least phi, either phi or xi is 1 and all that stuff, we know all these things. Now, it is like the old system. If phi is an expression of category T and u is a variable, then all u phi with respect to m g is 1. The value of all u phi with respect to m g is 1 if and only if for every value assignment g prime such that g prime is exactly like g except for the individual assigned to g prime, phi m g prime, that is phi, the value of phi with respect to m and g prime is 1. So, this is the formula for all, and similarly this is the formula for sum. We have seen this several times. So, I do not think we should repeat. Finally, whenever we have some g, we have to have these general rules, truth conditions for the formulas relative to m, because g has to go. If we remember that, so when we start checking, g is the starting point, but we touch upon all g primes and g double primes and all that stuff, we get back to g, but there could be anything, right. We could start here. So, but it so happens accidentally or whatever, it so happens that anywhere you can start, it is the same thing, but it has to be recorded as a rule. So, we do just one computation, by that we cover all the paths. So, the whole path is actually the satisfaction. So, the m means we have taken all paths, but all paths are taken by considering one path. If you see the old classes, then you can, if you can refer to the old classes, you can understand this better, and then this is for 0. Now, this precisely means some of the, we will go to the next language in the next class. I just want to determine some types, so that we understand the type theoretic things and also the elements and everything. So, for example, I need to determine something like the type. I do not know the structure of something, but I need to determine the type of, say, harmless. So, I can say that John smokes harmlessly or restlessly, whatever. What will be the type of this restlessly? Definitely the whole thing is T. I know that because it's a statement, and definitely it starts with this N and the rest structure. I don't know what it is, and it's not my problem. Let us call it Vi, and then here in this case Vi is slightly complicated. here this Vi is actually two things. It's a very different constructions. I would say it is actually, we call it just V, and there is an N. So what will be the type of, and this V once again takes two things. We'll see the structure of it, how we can structure this. So this will be John, this will be smokes restlessly. Now this Vi has got another Vi and an adjective, right? So if you want, you can call this Vi prime. So the Vi is smokes and the adjective is restlessly. What is the type of this? Ignoring other things, we can just determine the type of this. How do we do that? You see, we know the type of John is E. We know the type of Vi prime is E to T. Otherwise, T could not come. So E and E. So T comes out. So the type of this thing, this node is, we know that it is E to T, and smokes we know for sure smokes is E to T. It's a 1 plus predicate, right? Then what will be the type of restlessly? Definitely it will be. See, it takes an E to T and yields another E to T. So any adjective would be the type E to T to E to T, right? So this is and we also will talk about this in details, why it could be something else. For example, why couldn't it be, why this analysis is not possible? For example, why couldn't we do T, then it goes to N, sorry, then it goes to another T. This is a bad analysis, and then it goes to an adjective. But this is a correct syntactic analysis. Correct means syntactically it seems fine, but actually it is not fine. And then T goes to N and Vi. So you could have John smokes, and then here restlessly. We'll see in the next session that a construction like this. So in that case, what would be the type? It's a wrong type, but what would be the type? It would be, this is T, this is T, so it would be T to T. So our question is, how is it we are assigning the type E to T to E to T to an adjective, not T to T? We will talk about this in the next session, and then we'll go to L type. Thank you.